Problem 2. This is a great problem. Put a star next to this one. This one is rare. This is maybe 1 out of every 10 problems will end up being like this. Maybe 1 out of every 20 problems. Okay, this is a kind of rare problem, but I wanted to show this to you. Notice that this is the acceleration. Because it's accelerating, this is Newton's second law. So we go ahead and draw this. I need you to recognize that even though a contact force was initially given this hockey puck, as it is sliding down the ice, it is not sliding down the ice with the hockey stick. So this is just simply moving forward. It has an acceleration going this way. It has a friction going this way. And there's no other forces acting on this. This is, by the way, a kinetic friction. If we set up the second law along the x-axis, we run into a problem immediately. We don't have the mass. That's okay. We have one force, right? Fk. Fk by definition is mu k times normal. The normal by definition, in this case, for an object that is on a flat surface, we say that the normal is equal to the weight. But recall that weight is equal to mass times gravity. So I can express a normal in terms of mass and gravity. I wanted to get mu by itself, so I divide both sides by m and g.
That's all there is to it. That's all there is to it.
I know the value of mu, A is 2.0 meters per second squared, and gravity is 9.8 meters per second squared. Notice that the units cancel out, and you're left with a value that's going to be unitless and less than 1. And that's what we predict. Problem 3. We identify this as a weight, and this is a force, and this is not a friction, this is a mu, and it's a kinetic mu, which means this is moving. It has an acceleration. This is second law. We said 18 newtons are pushing it this way. It experiences a friction, a kinetic friction. You have a weight going down, which is 20 newtons, and you have a normal going up as well. If you want to get into a good habit, always if they give you the weight, find the mass, and if they give you the mass, find the weight. You can just do that automatically because you're going to end up using both of them anyway. So in this case, if you want to take the time to find the mass, you would divide this 20 newtons by 9.8, and the mass would end up being 2.04 kilograms. If you want to just, for the heck of it, to simplify it, we could just call it 2 kilograms if you want. If we set up let's pick up positive and negative. So I'm going to pick, if this is accelerating in this direction, I'm going to make this be positive and this be negative. If we do this along the x-axis, right, we're going left and right, I end up getting that 18 newtons minus Fk is equal to 2 kilograms times acceleration. We're looking for the acceleration. Now, the friction is going to be mu, which is 0.4, times the normal, which is the same as the weight. This results in 18 newtons minus 8 newtons. This results in 10 newtons. You should know that a newton is a kilogram meter per second squared. That means the kilograms cancel out. I get 5 meters per second squared. If you ended up using the 2.04 kilograms for the mass, it ends up being 4.9 meters per second squared. Okay, they're both close enough to each other. For your summary, what is the normal equal to on a flat surface as shown in the last 2 problems? Explain.
That's all there is to it.
Problem 4. We have 6 books in a stack. Each book weighs 3 newtons. The coefficient of friction between each book is 0.1. However, the problem is asking us to move the top 5 books off of the bottom one. So we're only interested in, here's a table, here are the 6 books. We're only interested in the interaction happening right here between these 2 books. We know that the mu at this point is going to be 0.1. So what we're talking about is what kind of force I have to apply to these books to go ahead and overcome this friction. And by the way, it hasn't started moving yet, so this is static friction. Since it hasn't started moving yet, this is an example of Newton's first law. And I have a force going to the right, and I have a friction going to the left. So if I move this around, I get the force required, if I add Fs to both sides, I get F is equal to the static friction. But by definition, the static friction is mu s times the normal. Mu s is 0.1. The big question becomes, what is the normal force? And in particular, what is the normal force for the top 5 books? So remember, if I had one book, the normal would be the weight. But if I put a book on top of that, it's going to increase the normal. And if I put 5 books total, that's going to increase that. So what I would suggest to you is that the normal for the top 5 books is going to be the 3 Newton weight per book times the 5 books. That's 15 newtons. So you have 1, 2, 3, 4, 5. Each one of those has 3 newtons of a normal. 3, 6, 9, 12, 15. That's a total of 15 newtons that are going down in weight, which means that it has to be a 15 newton normal going up against it. So that's going to be 15 newtons. If I multiply these two, I get 1.5 newtons.
That's all there is to it.